David Smith here with one more flipped classroom math lesson. 3 tips. First, you can adjust the playback speed faster or slower as you desire. Second, you can pause the video at any point to catch up with your notes or jot down some questions. Third, you can turn on the captions and read my words on the screen. Today's topic, limits of sequences. So we're going to dig back and take a look at sequences. My hope is that you've dealt with sequences in the past. If you haven't, you might search YouTube to find some introductory lessons on sequences. I am going to show you what you need to know to take these limits. So follow along. So check this out. Here's how I might state or describe a sequence with notation. A sub n is equal to 1 over 2 to the n. So what we do is this is our term notation, right? So a sub 1 would be our first term in this sequence of numbers. So our first term, we're just going to put that 1 in for n in our expression, function, and we're going to get, for a sub 1, it's 1 over 2 to the 1, which is just 1/2. Similarly, a sub 2 is just 1 over 2 to the 2 squared, which is 1/4. Okay, so that's notation for a sequence. Now let's take a look, let's write out this sequence. Sometimes that's helpful to do. So this one, our first term was 1/2. Our second term is 1/4. Our third term, when a sub 3, is going to be 2 to the third, so that's 1/8. And you can just see, this is sort of like our doubling function. We're just doing 2 to a power. So it's just going to continue on doubling on the bottom of our fraction, dot, 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 like that. Okay? The sequence goes on forever, right? It's a sequence of numbers. We can take it to positive infinity as far as we want. So, check this out. What's the limit of this function as x goes to infinity? Actually, let's change this. I'm used to using x's because we're doing more algebra-y stuff. This is really going to be an n there. So as n goes to infinity, what's the limit of 1 over 2 to the n? What's happening to this fraction as you go out? It's getting smaller and smaller and smaller. It's still positive, but it's going to get really, really close to 0. So it's approaching 0 from the right, and so our limit here is going to be 0. Okay? So there's an interesting concept that comes up here. This sequence converges, gets closer and closer to 0. So this is a convergent sequence. And you'll see in a minute that we need that for there to be a limit. Otherwise, there's going to be no limit. So let's look at one of those. Limit as n goes to infinity. Now we don't have a fraction, we just have 5 to the n. So as n gets bigger and bigger, this number is just going to keep growing. So this is no limit. Remember before what we talked about, this expression is unbounded. It just gets bigger and bigger. So this is called a divergent sequence. So there's no limit with a divergent sequence. It just goes and goes and goes. Gets bigger and bigger and bigger, or smaller and smaller and smaller, or bigger in the negative direction, but it doesn't approach a number, so there's no limit. Okay, let's do one of these. So this is going to combine what we just learned about sequences with the algebra involved when we were analyzing the limits in our last lesson. So here's our expression, again a fraction. So think about what you might be doing here. That's right. We're going to divide by the highest degree, in this case n, but before it was x. So we're just going to divide by n over n. We don't have any powers in this limit. So we're just going to divide by our highest degree on our variable. So we just divide by n over n, and I'm going to make my big old fraction. It's 2n over n plus 1 over n for that part, and this becomes n over n plus 4 over n. And now we can simplify that down. 2n over n is just going to be 2 plus 1 over n, bring that over. N over n is just 1 plus 4 over n, bring that over. Now we can run n to infinity and see what we get. So check this out. This just stays 2. Boom. When n goes to infinity, this fraction goes to 0. this just stays 1. When n goes to infinity, even though the 4 is bigger than the 1, this term still goes to 0. So that's plus 0. So this is just 2. So the limit of this expression, of this sequence, as n goes to infinity, is just 2. Now, if you recall from the last lesson, we can look at these expressions and analyze them by their degree. So the degree of the highest power in both of these expressions, the top and the bottom, is the same. It's just 1. So now we know that they are the same. That means it's just going to be the coefficient on this over the coefficient on that. There's a 1 there. It's just 2 over 1, which is indeed what we got. Just remember, you're on the hook to do this algebra. Okay, another one for you to try. Before we do the algebra, let's just take a look using what we know about how these expressions work. Which has the higher degree, the numerator or the denominator? The denominator has the higher degree. So when the denominator has a higher degree, what's the limit? It's 0. Okay, so let's do the math out here and confirm that. Actually, pause the video right now and use the same tricks that we've been using to analyze that. Okay, let's see how you did. We're just going to divide by the highest degree in the numerator, in the denominator. So that's n squared over n squared, because the highest degree in the denominator is this one. So now we're going to do our plug-in step. 2n over n squared plus 1 over n squared all over n squared over n squared plus 4 over n squared. Now we can do our cancellation. This is just going to be 2 over n. We're going to cancel out the n from the top, lose the squared there. This is going to stay 1 over n squared. This is going to go to 1 plus 4 over n squared. So now we've simplified all these little mini fractions so we can analyze our limit. So as n goes to infinity, what happens to that term? That goes to 0. What happens to that term? It also goes to 0. So now we know we have 0 on the top. We just need to finish out to check. My 1 stays a 1. This is going to go to infinity. So this is going to be 0. Okay? So this expression, this sequence, has a limit as n goes to infinity of 0. Okay, let's look at one last limit here. So check this out. Limit as n goes to infinity, a sub n, 2n squared plus 1 over 4n squared. So now I'm going to skip the algebra here and just use what we know about these sequences. Okay? The degree is the same. Okay? So now it's just going to be the coefficient on the highest degree term on the top over the coefficient on the highest degree term on the bottom. So that's going to be 2 over 4, which is just 1/2. So that's our limit for this function. We could do all this algebra, and don't forget, you need to show me that you can do that for some of the problems, but I'll also have problems that just say, evaluate the limit, tell me what it is. Let's take a look at that sequence, okay? So I just created this section here by putting in 1 for n. I got 3/4, so that's the term a sub 1, this is a sub 2, this is a sub 3, this is a sub n. Okay? So when you plug in 2 for n, this is the fraction that you get. When you plug in 3 for n, that's the fraction that you get. And you can see that we're approaching 1/2. We're not really there. 18 over 36 is 1/2, but we're getting closer to it. So we end up with n over 2n, which gives us our 1/2. So that's just a little look to see how the sequence itself is approaching 1/2. And don't forget, you can do this. You can plug numbers in to your function and just take a look at the sequence. That might give you a clue you need to solve a tricky problem. Okay, let's do a complex one, okay? So you can't really figure out what the limit is by looking at coefficients because this one is kind of scrambled up. We have a bunch of things that are happening. So we are forced to use some algebra to get this function, this expression into a place where we can actually pull the limit out of it. So let's just do that. First thing I'm going to do is I'm just going to distribute this fraction on that fraction. So this is going to give us 8n times n plus 1 times 2n plus 1. So that's my new top. My bottom, pretty simple. That's just going to be 6n cubed. Now there's a bunch of ways to evaluate the top. What I'm going to do is I'm going to expand this binomial here. So let's just carry on down. I have 8n times, now this is going to be 2n squared plus 3n plus 1. And then my bottom is going to just bring down my 6n to the third power. Now I'm going to reduce down. I have these two terms. They can be reduced pretty easily. So this would be 4n times 2n squared plus 3n plus 1 all over 3n to the third. Okay, so 8 over 6 is just the same as 4 over 3. And keep in mind that if you work this problem, you could do different steps, you could combine different steps. As long as you do your algebra correct, you're going to wind up at the same result. Okay, our next step is to distribute this term on these three terms on the top of the fraction, and then we can analyze our limit. So check this out. It's going to be 8n to the third, that's these two, plus 12n squared plus 4n. So that's the top. Now our bottom is just 3n cubed. So let's take a look at this. My degrees are equal. Okay, so this expression has degree 3, so does this. So then when we analyze our limits, it's just the coefficient of the highest degree term over the coefficient of that same highest degree. So this is just going to be 8 over 3. That's our limit. Now that you've watched the video, take a moment to jot down some notes, some questions, or a quick summary of the content. You can also re-watch the portions of the video that were a little bit challenging. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.